Hello and welcome to Lesson 1 of High Performance Data Manipulation with SAS DS2. In this lesson, we'll introduce the basic DS2 concepts. We'll introduce the SAS Viya Cloud Analytics service with its parallel processing capability. And then we'll set up our virtual lab image so that we'll be ready to do demos and practices later in the course. So let's get to it. So just what is DS2? DS2 is a relatively new programming language at Base SAS. It has a syntax that combines the best of the data step processing language with SQL. The DS2 is easily extensible, and it provides a kind of object-oriented approach to programming, if you desire, that can lead to some advanced data processing techniques. If you compare the two programs that you see on the screen, you can clearly see the bones of the traditional Base SAS data step still exist in the DS2 data program. DS2 does provide us with some superpowers. And the first one is that DS2 can handle most of the ANSI data types natively without having to have them down converted to double precision numeric or fixed width character. In addition, DS2 provides a simple mechanism for extending the language. This means that you can write your own methods for DS2, package them together, and reuse them very easily in subsequent programs. Now, the traditional Base SAS data step is single-threaded. That means that it reads from a single thread and computes on a single thread on your computer. Most modern computers have multiple CPUs available, which means that they were capable of handling multiple threads. And DS2 sees this as an opportunity to process more than one row in parallel. So on a traditional Base SAS platform with no other software installed other than SAS, you can use DS2 to process more than one row of data simultaneously in multiple compute threads. You will note that there is still only a single read-write thread in this particular mode. However, DS2 also has the capability of porting itself to other larger platforms. For example, there is a product called the DS2 SAS In-Database Code Accelerator, which allows us to take our SAS code, the DS2 code that we've written, and execute that threaded, fully distributed across a massively parallel processing platform such as Hadoop, Teradata, or Pivotal Greenplum. This produces multiple compute threads and also multiple read-write threads, dramatically improving process throughput. But SAS Viya also provides a massively parallel processing platform with this twist. The data is loaded once into RAM, and then it can be processed again and again in memory without having loaded it back to disk. This means that we do our massively parallel processing on memory resident data, and the throughput on this is really impressive. Now, you write a DS2 program in many ways, but in this class, we're going to use Base SAS as our client, if you will, for writing DS2 programs. And to do that, we'll use proc DS2 in a traditional SAS programming environment. DS2 programs can be executed right on the SAS compute server in single machine mode. In a single machine mode, you can still have multiple threads of compute process going, but there will be a single read-write thread. This is called symmetric multiprocessing. In database processing, allows us to take the code and run it where the data lives, rather than having to bring the data to the SAS platform as in a traditional SAS access. This allows us to run our code on that massively parallel processing platform and reap all of the benefits of parallel compute and parallel I/O. Using SAS Cloud Analytic services, we can do that same MPP-type processing on memory resident data, improving the throughput even further. Now, you may realize that the SAS live name engines that we use to access data in SAS always convert the data into fixed width character or double precision numeric. We'll be wanting to avoid that when we're processing in DS2, because DS2 has the capability of handling the rich data palette that are found in most relational database systems. In order to accomplish this, DS2 uses a separate driver to access its data. And this means that while we have drivers written for many data sources, not every data source that is supported by SAS Access has a driver written for it yet. Now, the list continues to grow with every mainnet release of DS2, so keep your eye on the online doc to see if yours is supported. And if your data source is not supported, of course, we have an ODBC compliant driver for accessing ODBC compliant databases that don't have an individual driver of their own. So when should we use DS2? I like to call this the shiny hammer syndrome. Once you find a shiny hammer, a new hammer, everything starts to look like a nail. But it's not true. You don't want to put the hinges into your door with a shiny hammer. A screwdriver is better. And for DS2, we want to think of it this way. Can my program make good advantage of this parallel processing capability? So for instance, if I'm running straight up on the Base SAS platform or on the SAS compute server, does my data processing have a lot of CPU involved? Because if the process is CPU involved, even though there's still only a single read-write thread, we could benefit from parallel compute threads. Or perhaps my data resides in Teradata or Hadoop or Greenplum, where I have the SAS in-database code accelerator installed. In that case, it's almost certain to improve throughput if I write my code in DS2. And if my data is in CAS, the DS2 is an excellent method of providing controlled parallel processing in this massively parallel environment on memory resident data. It's not always about performance, though. For instance, if you're calculating the U.S. national debt today, a traditional double precision numeric does not have enough digits of precision to calculate the debt to the nearest penny. If you're doing accounting, you may want to use DS2 just for the accuracy that you can achieve or the precision. And as you use DS2 more and more, you may have accumulated a large library of user-defined modules. And with these packages available, you can easily build larger and more complex programs in DS2 by simply reusing the modules of code you've already written. In this case, computer programmer efficiency may be the key. But if your process doesn't meet any of these criteria, it's unlikely to benefit from being converted into DS2, and it may actually run slower. For instance, the traditional Base SAS data step is a very mature and well-optimized process. And if your code is I/O bound, writing that process in DS2 will probably degrade the performance because the data step only has to manage one thread, while DS2 will manage multiple threads without the benefit of any speed on the compute end. Where DS2 will have to manage multiple threads, and because the compute threads are not the bottleneck in this case, performance will actually be worse in that. For example, the traditional SAS data step is a mature technology that is well optimized for its environment. If the process that you're using is not CPU bound, but is I/O bound, instead, the data step is more than likely the most efficient way of processing that. Using multiple DS2 compute threads on an I/O bound process only adds the complexity of having to manage those multiple threads without giving you any additional speed in the bargain. It may actually reduce the throughput of your data. Now in this class, some of our processing will be done in SAS Viya on the open cloud-enabled analytic runtime environment we refer to as the SAS Cloud Analytic Services, or CAS. CAS provides an amazing platform for dealing with data that's preloaded into memory and can stay in memory while you process it with subsequent steps without having to be loaded to disk in between. This makes your processing run extremely fast. And SAS Viya, or CAS, includes technology that allows you to handle data of any size, even if it's larger than the memory you have available to you. SAS Viya and SAS 9 are both vital parts of our SAS platform. SAS Viya makes a lot of data sources available to you through this CAS. You can store those data offline on premises or in the cloud. The data can be structured or non-structured data. You can have SAS data sets. You can save your SAS data in a special file called SAS HDAT on the server side, which makes the loading into RAM extremely fast also. Now, Cloud Analytic Services can be arranged in a couple of different formats. The first and most powerful format is the massively parallel processing format. And this allows you to use multiple machines in concert together to provide one giant compute engine. As a general rule, there's a server controller and several server worker machines. And on each of these machines, for instance, the server controller would spawn a session controller process, which would control worker sessions on each of the worker nodes. You're connected to the session controller from your client, whatever that may be. In this class, we're going to be using SAS Studio to connect and talk to this, but you could do this from Python or many of the other things, Java. And we'll submit our code to the session controller, and the session controller will distribute the work to the worker nodes where it'll be parallel processed. Another configuration for SAS is a single machine configuration we refer to as symmetric multiprocessing. In this case, the server controller and the session controller with its workers all live on the same physical hardware machine, but they utilize multiple CPUs on that machine to provide multi-threaded processing. And once again, this is a lot faster than a typical single-threaded process. So that you could use many different programming interfaces to get to SAS Viya. You could use SAS Studio, Enterprise Guide, the SAS windowing environment, depending on the version of 9. But there are many other coding clients that can be used to run code in Viya on SAS. No matter how you do this, you have to start a SAS session, and then you'll access a SAS library through that SAS session. It's referred to as the active library, and there's only one active at a time, but you can shift around as much as you like. And then you load files into memory in that SAS library and do your processing. You can process as many steps as you want. You can choose to leave them in-memory tables in memory, which is a very safe procedure here as the system is set up to be redundant. Or you can save those in-memory tables back to disk anytime you want. And then when you're done, you terminate your SAS session. In our classroom environment, we're going to have basically 2 machines. One is a client machine, which is hosting in Windows your SAS Studio, and all the other is the SAS Viya environment, which includes the session controller and a symmetric multiprocessing version of SAS. Hello there. So now that we've completed setting up our virtual labs for the rest of the class, let's go ahead and take a deep dive, or a deeper dive, into DS2 itself. We'll take a look at basic DS2 syntax. We'll compare DS2 data programs to traditional data steps, and then we'll finally try converting an existing data step program into a DS2 data program, and all of that coming right up. Now, DS2 is a little bit more structured than your traditional Base SAS data step. Like most new languages in SAS, DS2 is implemented in a procedure. So we see the proc DS2 statement here and the quit that terminates processing the code as if it was DS2. Within the DS2 procedure step, we have program blocks that define what type of program we're writing. They all begin with a keyword and end with the end of that same keyword. For example, a package program begins with a package statement and ends with an end package statement. A thread program begins with a thread statement and ends with an end thread statement. A data program begins with a data statement and ends with an end data statement. You will notice that each one of the program blocks is followed by a run statement, which is required syntax. Proc DS2 uses run group processing, which means that you can write multiple programs before you quit the procedure, but every program step that you write must be followed by a run, or it will not execute. So as we said before, the DS2 data program begins with a data statement and ends with an end data statement, and requires a run to execute. Inside of a data program, there are methods. Method blocks are named executable blocks of code. This method is called init. The method statement names the method, and the end statement terminates the method definition. In DS2, every executable statement that you write in your code must be part of a method definition, or you will get a syntax error. Now, DS2 includes some system methods. System methods are executed automatically and so are not executed when you call their name. The init method runs once at the start of your execution of this data step or data program. The run method runs once for every row of an input data set. And in this case, the banks data set in the DS2_SAS library has 3 rows of data. That means that the run method code will execute 3 times. And finally, there's the term method. The term method executes once and only once at the end of your data program processing. Only the run method includes an implicit output. And so traditional data step programmers will be most comfortable with the run method, as it operates almost exactly like a traditional data step program would. Now, because these methods execute automatically, every DS2 data program must include all 3 methods. But you don't have to write code for every method. If you don't provide code for a particular system method, the compiler inserts a null method on your behalf, and that means basically the method statement defining the method and an end statement with nothing in between. This is required because the init method must be there to start execution when the data program starts execution. And the end statement of the init method not only terminates init, but it calls the run method. And the run method needs to be there because it's going to be called by the init method. And it starts when called by init. At the end, you get an implicit output and an implicit return to the top of the run method. And this will loop until there's no more input data. And when it's all out of data, that end statement in the run method will call term. Now, the term method has to be there because it's going to be called by run. It starts only when called by the run method, executes the statements contained within it once and only once. And at end, it terminates the data program processing. So you can see why all methods are required. And for ease of coding, the compiler will supply you a null method for any method you don't write code for in these 3. Now, if you write a DS2 data program that contains none of these methods, that program cannot execute because there's nothing to start the process off. All right, to see if everybody was paying attention, this is the init method. It has a set statement that's reading the bank's data set. We already said that banks has 3 observations in it. So how many times would that method be executed? Think about that. Remember that this is the init method, and so the init method executes once and only once. The set statement will execute, of course, and it will read in the first observation from the bank's data set. But then it will never execute again because this is init. Now, besides the system methods, you can write user-defined methods. And user-defined methods can have arguments. Notice that in the parentheses here, we've defined an argument, a double precision numeric value called TC, that we'll use as input to this method. And it can also return a value. You notice that the definition says it's going to return a double precision number. And then down here in the code, the return statement actually does that. It sends back the computed Fahrenheit value after the method has processed the input. Now, user-defined methods only execute when they're referenced by name, but you can reference them as many times as you'd like. So in this do loop, we are calling the C to F method several times, and you can see that it executed once for each call of the do loop routine. Now, I've talked about executable statements, and we said how all executable statements have to be part of a method definition. That leaves the declarative statements. What about declaratives? Well, declarative statements in SAS, if you ever took the Programming 1 class, we usually talk about these as the compile time statements, or ones that only matter during compile time, right? And the declarative statements are used to set up the process before the processing starts. In DS2, there's 2 types of declarative statement. There's a global declarative that affects the entire data program, and there is a local declarative that only affects the method in which it's defined, right? So any global declarative statements must be in the data program before the very first method statement, before you start defining any methods. And if they're located anywhere else, you'll get a syntax error. For local declaratives, they must be in the method before the first executable statement is seen. If not, you'll get a syntax error. And to be honest with you, these two are what we call a declare statement. And within a method, the only declarative statement allowed is the declare statement itself. So let's take a quicker or a deeper look at the declare statement. The declare statement allows us to declare variables or temporary arrays. The declare statement assigns a data type, a length, and any other attributes that we care to assign. So you can see that the declare statement can be written out as declared or abbreviated as DCL. Being a man with very fat fingers as far as typing is concerned, I prefer the DCL. And notice that the very next thing you have to say is the data type. Those of us who are L-time SQL programmers are going to have a little trouble with this at first. We're used to saying the name of the variable followed by the data type. But in DS2, the data type comes first because you can then follow it by a name of several variables, not just one that you want to create with that single declare statement. Optionally, you can add a having clause. And the having clause allows you to apply labels and formats and informats to the variables declared in that particular declare statement. Here are some examples. A declare statement that declares 3 double precision numeric variables. It would be the same as a SAS numeric, if you will. And using the having clause, we've applied the $12.2 format to all 3 of those variables. Here's a different declare statement, declaring a high precision fixed point numeric value, a decimal type, with 35 digits of precision, 5 reserved for the decimal portion. And we're only making one of these called var1. And finally, a declare statement for a fixed width character variable, char25, named var1, with a label, my text. The declare statement is used to declare variables or temporary arrays and assigns the type and length of attributes. So a declare statement used in the global declarative space declares a variable with global scope. A declare statement within a method definition declares a variable with local scope. Although I don't highly recommend doing this in your actual program, you'll notice that we have 2 variables called myvar. One is a double precision floating point numeric. The other is a fixed width character variable. In a traditional data step program, this would be impossible. But in DS2, because this one is global, available to other methods, and this is local, available only to this method, these 2 variables with the same name can peacefully coexist. And then there's the problem with undeclared variables. Now, what is an undeclared variable? Well, it's neither read in via a set statement nor defined in a declare statement. That makes an undeclared variable. Undeclared variables by default have global scope, and they produce warnings in the SAS log. If the program cannot tell from the context what type of variable it should be, it will make it a double precision numeric by default, just as it would have in a Base SAS data step. If the context indicates that there should be a character variable, it will be fixed with character again, much like would have happened in a Base SAS data step. Local variables are declared local to the init method here and available only to init. Globally declared variables and undeclared variables both have global scope. And that means that the values for those variables will be available anywhere in the data program. We can see an undeclared variable here and a declared global variable here. Locally declared variables are available only to the method in which they are declared, and so they're local in scope. This has other implications. Global variables will appear in the program data vector, and therefore, by default, they'll be included in the result set. Local variables are never in the program data vector, and so are never included in any result set produced by a DS2 data program. Now, as we previously noted, there are many statements in DS2 that have the same function as they did in the Base SAS data step. For example, You can use a set statement to read in one or more data sets into your data program in DS2. With a by statement, by group processing works very much like it did in traditional data step, including first out, last out processing. Do groups and do loops work like they did in the Base SAS data step, including the do I equals with a discrete list of values, which, as far as I know, is unique to SAS programming. Loop flow control statements like continue, leave, and end, and all the program flow statements like return, output, and go to, stop, all work the way you would expect them to work in DS2. Declarative statements like drop, keep, and retain also work like they did in the traditional Base SAS data step, but remember that declarative statements like these in DS2 are global statements and must come before you begin your method definitions. Now, one thing that looks a lot the same but works significantly differently is the merge statement in DS2. Like in the Base SAS data step, you can merge two or more tables using a merge statement, but unlike a Base SAS data step, you don't need to sort the tables first. And also, unlike a traditional data step, the by statement is required in DS2. Lack of a by statement in a merge situation will result in a syntax error. Now, initially, the merge statement worked significantly different from data step. It also worked different from an SQL outer join. Recent additions to the DS2 language have included the retain option for the DS2 merge statement that makes it work just like the data step merge statement worked. In this demonstration, we're going to be taking a look at how the DS2 merge statement works versus a traditional data step merge. We're also going to compare it to an SQL full outer join, just so you can see the difference between that, the data step, and the data program. In order to do this, we're going to use these four temporary tables. You notice that table A and table B have unique values for the rows in the ID column. So joining table A to table B will result in a one-to-one type merge. Table C has multiple rows for the ID number 2. So joining either A or B to table C would produce a one-to-many type situation. And finally, table D has multiple rows for a couple of the IDs, and therefore joining tables C and D, or merging them, will produce a many-to-many type situation. So let's go back into the code and take a quick look at how we might do this. The first one is a data step merge. We're going to do a one-to-one merge using tables A and B. We're using the in-equal variables, as we learned in Programming 2, so that we can tell whether there is a merge for this particular row of data or not. And rather than selecting just those rows that merge, I'm going to actually write the values of those variables into two new variables called in A and in B, so we can see how the in-equal variables are working in the data step merge. We're going to do the same thing in DS2. I'm going to do a merge on the A and B tables by ID. I'm going to write out the values of the in variables. And when we're done, I'm going to do that again using the retain option on the merge statement. This is the one that is intended to make the DS2 merge work just like a data step merge. I'll go ahead and run those. And we'll see that we ran without any errors. Back in the code, I'm going to use ProcFet SQL to do reporting. I'm going to report on the data step merge and the DS2 merge, but I'm also going to conduct an SQL full join at the same time so that in the report, we'll see the results for the two different types of merges and for the SQL join. So we're using the data step kind of as our baseline comparison to see how everything else compares. You'll see that the SQL full join, when we try to mimic the in A and in B, we get pretty much the same result as we did with the data step. And the truth is that in DS2, the default merge produced the same exact output as the data step. So in a one-to-one situation, all three of these processes produce the same result. If we go back into this and try this with a one-to-many situation, that's A and C, we're going to run basically the same programs, doing the merge for DS2, SQL, and Base SAS data step. We'll take a look at the comparison of those results. And here we'll see that the data step and the SQL full join again produced the same result set. So a one-to-many, same result. But DS2 did not. And here's where the DS2 merge starts to diverge. You can see that for the by groups, even though there's a match, the value for table A is not carried down. So unless there's a second row involved for both data sets, then the value from the table that didn't have an additional row of data in it, that value does not copy down. That produces quite a different result set than we might have expected. Now we can go back into a DS2 and run this in a one-to-many merge with the retain option and run that same report. And when we do that, we should see that this makes the results the same with retain as they were in data step and in the SQL full join. So that retain option is important if you want the output to be similar to the output you would have got in a traditional Base SAS data step. And finally, there's the many-to-many situation. Now, if you all remember, in a many-to-many situation, this is where SQL stops producing the same result set as a traditional Base SAS data step because of the Cartesian way that SQL approaches joins. So in a many-many situation, there are multiple outputs for those rows that matched, where in a data step, there's only one row for the two rows that matched. Right? In DS2, with the retain option, we get the same output as the data step did. So once again, that retain option is critical. If you use retain and you run a DS2 merge, you'll get the same output as a traditional Base SAS data step. And finally, just to show you that without the retain, things are radically different. You can see that the in variables are not working the same, and again, that copy down isn't working the same. And this default output matches neither the data step nor the SQL full join. So, things to carry away from this is it's important to use the retain on the merge statement in DS2 if you want to get the same result as you did in a traditional Base SAS data step. Now, I have one more thing I'd like to show you, and that is what happens to the rows within our data that are not part of the by statement. So I'm going to produce another couple of tables that we're going to use in a merge. We're going to go ahead and merge these things with a retain option in DS2 and data step. And then we'll look at the source tables and the result of those merges as we go out. And over here, you can see that these tables have a many-to-many situation involved with them. But within the rows of the original table, say for all the items in ID2 group, they were in order 1, 2, 3. And for the items in the 3 group, they were in order 1, 2, 3. And in the table F, within their group, they were in order A, B, C, and so on. In a traditional Base SAS data step, the row order is maintained when you do this merge. And so you can see that within the groups, the order 1, 2, 1, 2, 3 is maintained, as well as the A, B, C. And because there was not 3 rows of data for the ID number 3, the B is the value that got copied down to the last row of the 3 group, for example. In DS2 with retain, there is no guarantee for row order other than the ID variables that you listed for the by statement. So you'll notice that when DS2 retrieved your data to do the merge for the 3s, the order of that second column, table E, was not even looked at. We don't care. And in this case, they came out in a different order, as well as the rows of table F. You'll notice that this one, the last of the 2 to read in was an A, so the A got carried down for the second one. And this is an important thing to note. It's a difference in the way that DS2 acquires its data, and there is no option to force DS2 to look at variables not on the by statement when it's doing a merge. So I just want you to be aware of that. And that's what we have for you on the DS2 merge. So this brings us to the point where I'd like to discuss what I call the subtle 7 dissimilarities between a DS2 data program and a traditional Base SAS data step. And the first one is that all executable code must be part of a method definition. Data sets are not overwritten by default. You'll need the override equals yet option to make that work. New variables are expected to be declared or you're going to get a warning. And remember that undeclared variables are global in scope and become part of the program data vector. The DS2 merge requires a retain option to produce results that are similar to the data step merge, but you don't have to sort your data before you do your merge. In DS2, the put statement doesn't have all those fancy line and column controls, so you can use format to position things as you would when you write stuff to the log, but don't expect the @ signs and slashes to work as they did in a traditional DS2 data step. And keywords are reserved words in DS2. It doesn't mean you can't name your data set data anymore. It just means that you'll have to indicate it's an identifier by surrounding it by double quotes. Which brings us to number 7, that ANSI quoting standard, right? That double quotes indicate the name of something or an identifier, and single quotes are used to delineate constant text. And as a result, we have a little trouble when we're resolving macro variables into DS2 code as a text literal. So we use that %tslit macro function to resolve the text and then put real single quotes around it so that it resolves properly and works properly in our DS2 code. You'll notice several less subtle differences between traditional Base SAS data step and DS2 data programs. And the more salient differences include the fact that you'll find several functions and statements available to you in a Base SAS data step that are not found in the documentation for DS2. And similarly, you'll find several functions and statements in DS2 that don't have a data step counterpart. So the truth is that most of the functionality of the data step has been retained in DS2, but the syntax can be different because it's been implemented differently. So some of the first things to address are some of the functions that we use a lot. If you're used to generating random numbers in a Base SAS data step using any of these RAND functions, as of SAS 9 M4, those functions are no longer supported in DS2, just the RAND function. And the RAND function can generate all of those distributions and more using a much more sophisticated random number generator. So that's the one that's supported in DS2. If you're a fan of regular expressions like me, you're used to using the PRX functions in DataStep to manipulate funky text. These functions were in the initial implementation of DS2, but are being deprecated as of SAS 9.4 M5. And the reason for that is the DS2 geniuses have produced 2 new packages, the PCRX find package and PCRX replace package, that ship with DS2. And they provide all the functionality you'll need for finding, matching, and doing replacements of patterns of text. But they work almost 10 times as fast as the original functions did. So use the PCRX find and PCRX replace packages instead. And finally, for those of us who are missing the diff and lag functions in DS2, they were added to the language in the M4 release of DS2. But there are still things that are not there at all. So the where statement, when I first tried to write a where statement in DS2 and it didn't work, I almost freaked right out. Interestingly enough, we have a fascinating replacement for this in DS2. And you'll notice here that rather than write a where statement, you can actually write, in curly braces, a complete FedSQL query. And that query will execute, including any of the clauses that you wish to contain. And the result set is processed directly in DS2 without having to be written to disk in between. You can do things like joins, grouping, anything you can do with a select type query, you can do here on the set statement and pass the results directly to the data step type language of DS2 for further processing. That's a pretty potent superpower. In DS2, I'm used to using update and modify statements to modify values of an existing data set with values from a different data set. If you're an ANSI SQL user, you may recognize the fact that's a very difficult thing to do in SQL. Generally, it involves a correlated subquery, which is horribly inefficient as far as resources go. And in SAS, this can be even more of a problem, as one of the data sets may reside on a platform that's different from the data that you're using for the update. For example, your update values may be coming from an Excel spreadsheet and being produced in a Teradata table. This has caused us to do all sorts of interesting things in the past, like read in the Excel spreadsheet, then push it up into a Teradata table, then do the join in Teradata. So we don't have to do that in DS2. We have a thing called an SQL statement package. And I don't want you to get hung up on the syntax right here, because we're going to spend quite some time with this later on. But basically, using the SQL statement package, we can read in data into the program data vector here, and then just execute an update statement specifically for each of those records in the other database. And this avoids all that cross-library overhead, and does not require any kind of a correlated subquery, so it runs really, really fast. Other statements that are missing are the trib, label length, format, informat statements. All of these are designed to modify the metadata of variables that we're processing in a data step. In DS2, we have none of those, but we do have the declare statement. Remember, the declare statement can use the having clause to change formats, informats, labels, that type of thing. And so while the length, labels, attributes, format, informat statements all have differing syntaxes, in DS2 we only have one statement, the declare statement, and the syntax is always the same. The next thing I discovered missing in DS2 was the array statement. I use arrays extensively in my data step programming, and I was very disappointed to think that I would not have arrays available to me in DS2, but it's not true. If you think about things, in Base SAS, we do two significantly different things with the same statement. This array is an array of PDV variables. It's pointing at a series of variables in the program data vector named N1, N2, N3, N4, so on. Now, this array is a temporary array, and it's not associated with program data vectors at all. It's just using system space to store some information for us in an array kind of format. In DS2, we approach this with two different approaches. The first one, array of PDV variables, is implemented in DS2 with a var array statement. Notice that really the only difference between this and the array statement was the requirement to specify a data type. So var array, double, and then N5. This will produce a series of variables in the program data vector N1, 2, 3, 4, 5, and it'll work just like an array worked in a traditional data step. For the temporary array, those arrays that have elements not in the program data vector, we had to specify the type, if you remember when we did this, and we had to specify temporary, and then the system took care of putting that out in the system space. In DS2, you just declare a multidimensional structure. So here I'm declaring the C array as a 5-element one-dimensional array, and it's character 1, and I get 5 elements stored in system space, just like a temporary array in the traditional data step. And like the temporary array in the traditional data step, whose elements did not appear in the program data vector because they are not associated with variables, arrays declared with a declare statement, whether they're global or local, in DS2, their elements are never associated with PDV variables, so they don't appear in a PDV either. And that's quite handy when you're using arrays as lookup tables. Now, there are some things that are missing from the data step that are missing in DS2. And so these are all statements associated with processing text files. And as of this course writing, right, DS2 still only reads and writes from tables. So it does not read text files. And that's why those statements are not in the DS2 documentation. Then there's another series of statements that we use in Base SAS to control the SAS session itself. Rather than the program, we're feeding back and controlling the SAS session. We can actually turn the SAS session off, affect the color of the log with display manager commands, those types of things. We can also execute operating system commands from DS2. Now, DS2 actually runs in a separate process from the SAS process that spawned it. And as a result, it gets information from the SAS system and it sends back your log, right? But it executes in a completely separate process. So it doesn't have any hooks to control the SAS session that spawned it or to interact with the operating system that SAS is operating in. We're going to see later on that the DS2 that the SAS started off might not even be running on the same platform. It might be running up in CAS. It might be running in Hadoop or in Teradata. And so I don't expect to see any of this type of functionality ever built into DS2. Hi, it's Mark again. In lesson 3 of high performance data manipulation with SAS DS2, we'll take a look at program structure in more detail. Also, we'll take a deeper dive into the different data types that DS2 can process. And finally, we'll look at some interesting functions that can be useful in our DS2 programs. So let's get going. Before we dive too deeply into the program blocks themselves, I'd like to talk about a particular global statement for the DS2 procedure. Now, DS2 procedure supports very few global statements that go outside of program blocks. And they're not global in the nature of the way we think about a global statement in the SAS system, for instance. A global statement in Proc DS2 goes before a program block, affects the behavior of processing for that block and that block alone. And as soon as the subsequent program block is finished processing, the option goes back to its default behavior. So we're going to look at DS2 options, which allow us to change some things that make it helpful when we're processing in DS2 for overcoming things like division by zero and for troubleshooting. So the first one is the div by zero equals. Now, the default behavior for div by zero is an error. In the old days, a traditional SAS data step, when you were running your program and everything was fine, and then all of a sudden a variable came into play with a zero in it that was the divisor in a problem, the program used to throw an error and stop processing. We call these data errors. In subsequent versions of SAS, they throw a note in the log, but they continue to process, just produce a missing value. Now, DS2 is very ANSI compliant, and ANSI systems don't allow division by zero. And so normally, if you get into a situation where the divisor is zero, then DS2 is going to throw an error and stop processing. If you wish to make this more like a traditional SAS data step, then you can set DS2 option div by zero equals ignore, in which case you won't even get a note in the log. A null or missing value will be produced and processing will continue. But the one that's most useful is type warn. As you can imagine, we'd said that DS2 supported 17 different data types. And those data types are invariably going to be used in multiple expressions that cause data type conversions to happen automatically in the background all the time. If we wrote a log error or note every time we did an automatic data type conversion for you, your log would fill up so quickly you wouldn't be able to see anything else. So by default, automatic data type conversions are ignored by DS2. No note or warning is written in the log, processing just continues. But there will be times when the automatic conversion causes issues with the way that your program is calculating results, and you'll be wanting to see that. So you can set this DS2 option type warn right before you run that particular step. And then every time an automatic conversion happens, you do get a warning in the log, and that can help you narrow down where the problem is occurring. Now we'll move into the program blocks themselves. And in the program block, we have that global declaration space that goes right before the first method definition starts. These statements are not valid inside of the method themselves, and they include retain, drop, keep, rename, and var array. The next thing we talk about is data types, and we said that DS2 could define and manipulate about 17 different ANSI data types straight up without any type of data conversion being required from the data source. This is true, and you can create those data types right in a DS2 data step also, but where you save the output or the result set to will control what you can actually write. So for instance, we may be running a DS2 data program in a pure SAS environment, and we have decimal data types and varchar and all those fancy ANSI types as we process them in a program data vector. But if we are writing that result set out to a SAS 9 data set, then before they can be written to disk, all of those data types will have to be down-converted by the engine to fixed width character or double precision numeric, because that's all that a SAS 9 dataset can store. For example, in Hadoop, if we're processing Hadoop data, Hive doesn't have an ANSI time data type. So if you're storing date time or date values, you'll get ANSI date and ANSI timestamp values in Hadoop. But if you store a time value, it comes out varchar on the Hadoop side. And many databases have differences like this. For example, Oracle stores date, time, and timestamp values. It stores them all as timestamp. So while we can process them, that's fine until you write them out. And then what can be written out is determined by the target data source that you're writing to. First, let's talk about character data types. DS2 can define and manipulate 4 different character types. The char and nchar are both fixed width, and the varchar and nvarchar are both variable length per row. In all cases, the n indicates the number of characters maximum that can be stored in the column when it's defined. In char and varchar, it's 1 byte per character. But for Unicode characters, particularly are used in languages that use 1 character per word, for example, like Chinese or Japanese, the codes are much more complex. There's a lot more of them. So generally, it's 2 to 4 bytes per character code. So n still defines the number of characters to store, but it may result in a larger amount of bytes on disk than you're used to. However, a DS2 can handle char and nchar in the same session, no matter what the session encoding is. Interestingly enough, we've just talked about character data. We've already talked about more data types than a traditional SAS dataset could handle, all told. The next data type I'd like to talk about is floating point numeric. And floating point numeric data types store assigned but approximate value with a floating point. These come in basically 2 flavors with a float kind of in between. Double precision numeric is the standard SAS numeric value. And in DS2, it's the standard value for an undeclared variable that you can't tell what type it is from the context. Double precision floating point values are stored in 8 bytes. And this means that you're going to get a maximum of about 16 digits of precision. Now, the magnitude you could store is enormous, but the precision will top out about 16 digits. A smaller version of this, the real, is only 4 bytes, which tops out about 7 digits of precision. And then there's float. Basically, you tell the float what precision you need, and it'll store the result in either 4 or 8 bytes, or either double or real. A DS2 has a different type of numeric involved with fractions. This is a decimal data type. This is an exact fractional type, whereas the floating point data types only promise you an approximation of the number that you stored. The decimal data type promises you the exact number that you stored. Of course, under the covers, it's going to use more bytes than the 8 bytes in your double precision numeric if you're storing some very high precision data. You can have up to 52 digits of precision overall in a decimal number. Now you think about this, this is significantly more precision than you could have got with a floating point number at only 16 digits. But because you're limited to 52 digits total, you're going to see that the magnitude limit on a decimal number is much lower than you can get with a floating point. I like to say that scientists and astronomers love floating point numerics because you can have numbers of enormous magnitude stored, and they rarely need more than 16 digits of precision. Whereas decimal data types are loved by accountants who like everything down to the nearest penny and don't want any of this approximate stuff But wait, there's more. There's integer numeric types. These store numbers but have no room to store a fraction. As a result, they store it in fewer bytes than a similarly sized floating point or decimal type. These range in size all the way from a tiny int, which is only 1 byte and can only store a number between a negative 128 and a positive 127, all the way up to a big int, which can store up to 19 digits max. Integer types always return an exact value if the number stored in them falls within the range that they're capable of storing. In ANSI systems, we also have date, time, and timestamp data types. These should never be confused with SAS dates, times, and datetime values. In SAS, all of those values are stored as double precision floating point numerics, and the only thing that distinguishes them from any other number is the format that you apply. So if you have the number 365, that could be my weekly rent. It could be the number of days in a year. It could actually be a date, right? And we wouldn't know unless the appropriate format was applied to that number. In ANSI systems, a date can only hold a date. It can't hold anything else. And a time can only hold a time, and a timestamp only a timestamp. And so they're not related in that way. And finally, DS2 supports 2 binary data types. Binary types are normally used to store things like videos and images and sometimes binary flag type data. These come in 2 types: fixed length binary data, where n is the total number of bytes you're going to make available, or var binary, which is variable per row, where n is the maximum number of bytes that can be stored in that particular column. In a var binary column, of course, only the actual number of bytes needed to store the value you store is used for each row. So for a quick review of traditional numeric value processing in Base SAS. In a traditional Base SAS data step, all numeric values are double precision floating point numerics. This means that they are assigned approximate values. They use a maximum of 8 bytes and provide a max of 16 digits of precision. You can see this when we try to stick a very large number into a SAS numeric. The digits all come out the same up to about the 16th place. And then when you retrieve the number, the values are kind of randomly different. In DS2, when you write a numeric constant, because the default for any numeric type is double precision, when we write a numeric constant in our code, it compiles as double precision numeric. We can see this when we print the values out, because once again, we're getting that pretty much a maximum of 16 digits of precision. Now, the constants get their data type assigned when you compile your code. So we need some way of flagging this number and telling the compiler, look, don't compile this constant, which isn't going to change during the processing, as a double precision numeric. I want this compiled as a decimal value so I can have that higher precision if I want it. And in DS2, this is done by following the constant value with an n. No quotes or anything required. Just follow the constant value with an n, and that will be compiled as a decimal value instead of double precision. And that can resolve the issue. Now you can see that we can put these larger numbers into our value, and because we've defined the variables as decimal and we've defined the constant as decimal, the value is stored precisely as we wrote it. Now, if you write a numeric constant that does not have a fractional value, it compiles as big int by default, which is a nice safe way of compiling it, unless, of course, the integer constant has more than 19 significant digits, in which case we need to think about that. How would you compile an integer constant with more than 19 significant digits without losing any of that precision? Well, remember that when we define a decimal value, we can tell it how many digits of precision we need, and we don't have to reserve any of those for the scale or fractional portion. So if you just use the n suffix and that large constant value, it will compile as a decimal value without any fractional portion. and you can store that up to 52 digits without losing precision. Next thing is we went to great lengths to explain how date, time, and timestamp values in ANSI systems are significantly different than SAS date, time, and datetime values. So how do you write a constant for an ANSI date, time, or timestamp? Well, you simply prefix the value with the word date, time, or timestamp so that the compiler has a clue, and then you follow that immediately with a quoted string, and the values have to be precisely formatted in this way. A date is always a 4-digit year, a dash, a 2-digit month, a dash, and a 2-digit day. Time is always formatted as a 2-digit hour using a 24-hour clock, a colon, a 2-digit minute, a colon, and 2-digit seconds. You can add a decimal point and up to 5 digits of fraction, if you wish, to a time value. Timestamps are basically a combination of the two formats above with a space in between them. The date in the ANSI date format, a space, and the time in the ANSI time format. And once again, if you have fractional seconds, you can add a decimal and up to 5 digits of fraction for your seconds. You can see that when we write them this way, they come out perfectly well understood in our DS2 program. So let's have a look at how this compiling of constants can affect the outcomes in our SAS programs in ways that we might not anticipate as traditional data step programmers. Here I have a typical data null step. I've declared 3 decimal variables A, B, and C. I've assigned values to them, and I'm printing them out in an attempt to see how well the values were stored or how close the stored values were to the values that I put in as constant. And when I run this code, as you might have expected, because the constants were not defined as decimal, they compiled as a floating point numeric. And as a result, we only got pretty close to 16 digits of precision. And after that, everything kind of went haywire. So you might think, well, we'll just fix this by adding the numeric indicator here, compiling them all as decimal, and then that should resolve the problem. And we go ahead and rerun this code. We can quickly see that it didn't resolve the problem as expected. Now, this is concerning, right? We've got a defined decimal variable. We have a defined decimal value that we stuck into it. And we have kind of every right to expect that the value stored there would be a decimal type with full precision. So somewhere in here, an automatic conversion is going on that I'm not noticing, that I don't detect. And it's causing me to lose the precision inadvertently. We discussed earlier that during automatic conversion, DS2 doesn't automatically put anything in the log. So we could add our DS2 options type warn, and this will help reveal where the automatic conversion is occurring. When we look at this, it says, look, you're getting implicit conversion of decimal to double in statements 91, 92, and 93. And if you look at those are the put statements that are writing the values out. You say, well, how could a put statement be converting my value? Well, if we look at the code, we notice that we have specified a format. Now, this is a thing that you might not think of as a programmer. We're used to applying formats at will whenever we want. But if you think about what is a format in Base SAS, a format is instructions on how to display a number. You say, well, what kind of a number? We've never had to ask that question before in traditional data step programming, right? But what kind of a number? Well, a Base SAS numeric, right? What are Base SAS numerics? They're double precision numbers. So before I can apply this format to the value, I'm going to have to convert it to double precision. So now I'm not losing the precision when I assign the value to the variable. I'm losing the precision when I display the value in the log. If this rationale holds true, I should be able to go back to my code, remove the formats, and then rerun that code. And without the formats, it should print the actual value that I expected. So let's test my theory. And voila. Notice that even though I left the type warn global statement functional, ran it again, there are no more warnings about automatic data type conversion. And we can see that the values stored in the variables actually were the values we expected. The down conversion was happening during the display of the variable. So that's kind of one unexpected result that we can get when dealing with multiple data types for numerics in DS2. All right, we talked about how we can manipulate all sorts of different types of data, but when we store the data, it might be something different. And we talked about thinking about what would happen if I use a numeric value in a character context and all of that type of thing. So what we're going to do is we're going to do some manipulations with data in DS2 to show you that it's capable of dealing with all these data types and handling most automatic conversions pretty rationally. So I've declared 3 numeric variables, decimal, double, and real, and I've declared 3 character variables to hold the actual values in there so we can compare the expected to the actual. And as I assign those values, then I write them out in the log. And hopefully, because all of the values are within the expected capacity of the data type that we're using, everything should come out as expected. And this means that even when I assigned decimal types to a real value, it all worked out as expected. As long as you keep the value within the range that the data type can handle, you pretty much get the expected results. And the last thing we said, well, we can handle these data types in pure data manipulation in DS2, but when we write them out to a data store somewhere, the data store may or may not be able to handle those data types. So here we're going to take and write these out to 2 different data sets, one SAS data set and one Oracle data table. We're going to declare those same values, real, double, and decimal. And we're going to write them out concurrently to both of those output data types. And then when we're done, we're going to take a look at the log and see from the notes what actually happened. And you can see here that although the data was decimal, double, and real during the processing, as indicated by the notes that we printed, when we wrote this data out to a SAS data set, the base driver said, hey, we can't store real data in a SAS data set. It has to be converted to double precision. Well, that's nice because that's actually higher precision than the real value was, right? Conversely, the decimal column can't be stored in a SAS data set either, and that was stored out as a double precision. And in that case, some of the precision would have been lost during the conversion. All right, if we look at the data types, we can see the actual values of the data type by reading the information from the database table and compare that to the actual value in the SAS data type, making a little report, okay? We see that the Oracle table values, the desired and actual values were all the same, but as we had suspected, the real value being up converted to double in SAS didn't cause any problems, but the decimal version being basically downgraded to a double precision numeric caused a loss of precision right around the 16th digit. And that, in a nutshell, covers numeric precision in manipulation and in storage in DS2. So as we discussed, because SAS dates, times, and timestamp values are stored as floating point numbers, they don't look like anything special if you just look at them the way they're stored. So how do we know what date, time, or date time value this might represent in SAS? Well, in SAS, we apply a format. And the format makes the floating point value look like a date, a time, or a date time value that's human readable for us. When we store these values out in a relational database in a traditional SAS environment, something has to happen because you can't store SAS dates basically out in a database and have them make any sense. In a database, you have ANSI dates. So when you read ANSI date, time, or timestamp values into SAS from a live name engine, they are converted to the correct floating point numeric value and assigned an appropriate format automatically. And when you save data to a database, if you have a floating point numeric value, a SAS numeric, that has a date, time, or date time format applied to it, when SAS writes that value back out to the database, it automatically converts it to the ANSI date, ANSI time, or ANSI timestamp value that corresponds to that SAS date numeric. And this has to happen because SAS data step has no way of processing these ANSI date, time, or timestamp values. It needs the floating point numeric to process, but the floating point number would make no sense at all as a date, time, or timestamp value in the relational database. Now, in DS2 programs, we're capable of processing ANSI and SAS values at the same time. So when we read in ANSI date, time, or timestamp values from a relational database, we read them straight up as the ANSI type. DS2 is perfectly capable of understanding and manipulating that type. When we read floating point numeric values from SAS datasets that have a date, time, or date time format attached to them, much like writing that value into a relational database, DS2 automatically converts those values into ANSI date, time, and timestamp values. So if you read in a SAS date, time, or date time formatted value, then DS2 automatically converts it to ANSI date, time, or timestamp. But what about a SAS numeric value that didn't have a format attached to it, and yet it did represent a date? Well, we provide explicit functions to convert the data from SAS floating point to an actual ANSI date, time, or timestamp, and the other way around. If you want to explicitly convert an ANSI time or timestamp or date value into a SAS floating point numeric, we have a function that can do that. And using these functions and understanding how things work when you read the data, you can process both ANSI and SAS datetime values in the same program. So the functions involved for these explicit conversions are these four here. And they're required because, if you recall, ANSI date, time, and timestamp values are non-coercible. That means you can't just, for instance, if you wanted to use one of the interval time functions in SAS, like int check or intNx, you need to provide a double precision numeric. If you read that value into DS2 from a SAS dataset that had a date format attached to it, then what you have is an actual ANSI date value. You can't feed that to the intNx or intCheck function. So you'd need to feed it to the toDouble function that would change it back into the appropriate SAS date or datetime value. And conversely, if you have a SAS double precision numeric that didn't have a format attached and you want it as an ANSI date, time, or timestamp, you can use the toDate, toTime, or toTimestamp function to convert SAS values to ANSI explicitly. And here's what that looks like. The toDate function accepts a single argument which must resolve to a SAS date numeric value, and it returns the appropriate ANSI date value for that. You can see here how that works. The toTime function accepts a single argument, which is a floating point representation of time in SAS, and it returns the appropriate ANSI time value for that. And toTimestamp, again, receives a single numeric argument, its floating point argument representing a SAS datetime value, and that is converted into the appropriate ANSI timestamp value. Going the other way, We take any ANSI date time or date time value and feed it to the toDouble function, and toDouble will pump out the appropriate floating point value that represents that date time or date time value in Base SAS. Hi there, Mark again. In lesson 4 of high performance data manipulation with SAS DS2, we'll take one last look at converting traditional data step programs into DS2 data programs. And then we'll leave that world behind. We'll dive into the things that DS2 does that the traditional data step does not. We'll take a look at user-defined methods and storing them in packages for easy reuse. We'll take a look at storing data step type processing in thread programs, and then reusing those thread programs from a DS2 data program to process multiple rows of data in parallel. And finally, we'll look at running our DS2 programs in SAS, SAS's amazing, massively parallel processing platform, working with data that's memory resident and is lightning fast. So I hope you enjoy the ride. In lesson 2, we first discussed translating existing data step programs into DS2 data programs. And we introduced you to DS2 procedure. We're going to use that same procedure now to convert a slightly different data program and go through the steps of making that program functional in DS2. So the program we're going to be working with has an array statement. We know that there is no array statement in DS2. There's a where statement. We know there's none of those in DS2. Has a new variable, obviously, that we're going to need to think about declaring, and the same with the queue. Right? There's a keep statement here that's probably in place due to us reading in a bunch of variables we don't need. We're just going to run this program to make sure that it works. And take a quick look at the output data to see that at the end, for each employee ID, we have total contribution for that employee. Now, if we were to process this in DS2, we might start out by converting the program with procDS to DS2. With that program completed, we run into the same issues we saw before. We need to add the procDS2 statement in the front. We need to end with a run and a quit. And we had this empty set of statements here that we didn't like, and say that looks a lot more interesting. Now notice, even though there's no array statement in DS2, procDS to DS2 successfully translated that into a var array statement, which was kind of nice. Also put it in the global space. It moved the keep statement out of the end of the program up into the global space of our output program. And again, we're going to see that we're reading in the employee donations, but the where clause got commented out. So we can fix this by using a fedSQL query instead of a where statement and a set statement separately. And we'll just select. We also mentioned that we're going to need to declare this total. So let's go ahead and add that. And honestly, there's this Q variable down here. We don't really want that in the output anyway. So I'm going to go ahead and declare that local to the run method. Remember, data type first, then the variable name. And we already expect contrib to be out there because we ran the data step. So let's go ahead and add the override equals yes while we're here. And that seems to have worked. Let's have a quick look at the output data set. We have employee ID and total for every employee. That's nice. And nothing in there otherwise than the QTR variables. And we could leave this code as is. Now, because I already have a select statement here, if you think about it, right? If I just selected only the columns I wanted to deal with, I wouldn't actually need a keep statement up there. So instead of reading in extra columns, let's just select. We're not going to need that keep statement at all. So let's go ahead and comment that out, just see how that works. And looking at our contrib output, we can see that we do have total employee ID and only the quarter variables were kept. So by a little bit of DS2 only magic, we've been able to declare the index variable for our do loop local and not even worry about bringing it out of the result set. And if we're going to write a select statement anyway, why not only read in the data that you need? And so this will be my final answer. I'll save this, and that would be my production DS2. So in an earlier lesson, we looked at a small little user-defined method, the C to F method. I'd like to take a deeper dive into user-defined methods now. Remember that the method statement gives your method a name, and it allows you to specify parameters that can be handled much like locally declared variables inside of the method code. Your method can return a value. You should say returns if it's going to return a value and specify the data type. And then in the method code, you'll have to explicitly code a return statement that returns the value in question. But your method can also modify some of its parameters. In object-oriented programming, we frequently refer to these types of parameters as being passed by reference. And what that means is, instead of giving me a value in this slot, I want you to give me the name of a variable. From the name of the variable, the method can figure out where in memory that value is stored, and then it can access the value directly to read it, but it can also write back into that area. So while a method that returns a value can only return one value, that same method may have several in-out parameters that allow us to modify several values at once. And you could either return a value or do in-out parameters or do a combination of both. For example, you may have a method that modifies several parameters and then returns a return code to indicate how the processing went. Now, these standard parameters can be passed in either as a constant value or as an expression that resolves to a value. That expression could be the name of a variable, or it could even be a formula of some sort that produces the value. And these work a lot like data step function parameters. Now, a value of one of these standard parameters is not modifiable. In other words, you could take the value in, but you can't pass it back out because it could have been a constant. You can't write to a constant. And if you're going to return a value, you'll only be able to return one value with a return statement. Now, in-out parameters are different. You're not allowed to pass in a constant value to an in-out parameter. The in-out parameter does not want to know the value. It wants to know where to find the value in memory. So we have to pass an in-out parameter of variable name. Once we have the variable name, then we can retrieve the value from that variable, but we can also change the value of that variable. So this works a lot like a traditional data step call routine. When you pass in parameters, they can either be scalar parameters or arrays. But because parameters are all treated internal to the method as if they were locally declared variables, you cannot pass in a var array. A var array is a global-only type construct. So how might we use this concept? It's traditionally used to standardize business practices throughout an enterprise. So for example, maybe we want to ensure that everybody calculates annual interest the exact same way. There's a lot of different ways of approaching this. We want to define a way of doing it that works for everybody in the company and is easily explained to our regulators, for instance. So we might look at this kind of formula. The amount we have at the end is equal to the sum of the original amount plus the amount times the annual interest rate. When we design this, we need to think about all the information we need to get in. So we need to get in an amount, a number of years, and an interest rate. In that case, our method's going to need 3 parameters. If we pass in the value of amount by reference as a variable, then that variable value could be modified directly in the variable we pass in. And so that's the first way we're going to design our interest method. We're going to use it with an in-out parameter for the amount. Other parameters are not going to be modified. We can pass them in as standard parameters. So the definition for the interest method might look something like this. I'm defining the interest method with an in-out parameter that's a double precision numeric. Now this is going to have a variable name on the outside, but internal to the method, we're going to call it amount. And it requires 2 other parameters as well, a double precision parameter named rate and an integer parameter named years for the number of years. Now, internal to the method, we're going to do a do loop that cycles through our calculation once for every year of the period the amount is on deposit with us. So we're going to declare a local variable I that we can use as the index variable. And it's very important that you declare your index variables local when you make user-defined methods like this. Otherwise, they can inadvertently wind up in the program data vector. And if there's another variable named I out there, it can cause all sorts of conflicts. But the ability to declare a local variable makes this a very safe process. So now we've declared the interest method. All that remains is to use it. Remember that when we use the interest method, the first parameter cannot be hard-coded because that's an in-out parameter. And so we're going to set up a variable called total and another one called duration. The total variable will give it the initial amount, so 5,000. The rate is a standard parameter. We're going to hard-code that at 4%. And the duration we're going to get from our do loop. So this is going to go for 1, 3, and 5 years. And each time we do this, we'll write out the duration, the total for that duration as a dollar amount. When we execute this code, we can see that our interest method is working well, and that holding my money for 1 year gets me 4%, $5,000 as my interest. And holding it for 5 years, we can see the effect of compounding that interest over a 5-year period. Now, management wants us to use this interest calculation for all of the programmers in the company. How could we best deploy this so that other people would be inclined to use it? You know how this goes. There's only so much you can do by laying down the law to programmers. You can tell them, you have to do it this way, and you better do it this way. But programmers are a gnarly little bunch, right? What's the way to a programmer's heart is to make it easy. Make it so easy to do it the way you want them to do it that it would be too much work to do it any other way. Now, in Base SAS, we might have thought of encapsulating this calculation method in maybe a %include file where they could draw in the code that did the calculation. But that involves variable names and things that won't be transparent in the code that we're using it in. So that might be problematic. We could also do this maybe as a macro that brought in the data step code required to do this calculation. But once again, that can be problematic because it also involves variable names that are not transparent to the user. And finally, we might think of using procfcmp. If you're not familiar with that, procfcmp is a function compiler, which allows us to write our own functions for Base SAS use. It seems to me that there must be a better way of doing this that doesn't involve including variables in my program data vector that I'm not aware of. So let me introduce you to the concept of user-defined packages. User-defined packages and user-defined methods go together like peanut butter and chocolate, right? This is the perfect combination. So a package program allows you to name a package that you store out in any SAS library, encapsulate any number of methods that you'd like, and when you run this package program, that package is stored in the library with all of the methods that you've predefined in it. And then to use that package in subsequent code becomes a very, very simple task without having to recreate any of the code for all of those methods. Just remember, if you store a package in the work library today and shut down your SAS, tomorrow don't expect to see the package there. This library is still the work library, and it will be deleted at the end of your SAS session. So better to store these in permanent libraries if you want to use them in a separate session. So a quick review of package program block. It begins with a package statement. It ends with an unpackaged statement. Global declaratives in a package work a little bit differently than global declaratives in a data program in that global declaratives are still private to the package. For those of you who are object-oriented, you'll recognize these global variables in a package as a way of keeping status of what's going on in a particular package's instance. You can think of a package as the class, if you will, for DS2 if you're doing object-oriented programming. Those global variables are available to any method within that package, but they don't affect anything outside of the package itself. And then, of course, as many methods as you would like can be stored inside that package. Those methods may have local variables of their own that are private to that method only and are not available to any other method within the package. So instead of putting the interest method code directly into our program, let's put it in a package. And last time we wrote this, we wrote it with an in-out parameter, and maybe that caused a little grief when people were using it. So we're going to recreate this so it returns a value just like a function would do. And that means that none of the parameters are in-out. See, there's the basis, the rate, and the years. Now we're going to return a double precision value, and here's the return statement that does it. Otherwise, the calculations in the code are pretty much the same. Now we've put this in a package statement, so when we run this code, it will create the package and store it in the DS2_SAS library, and the element in there will be called my_methods. So the package hasn't actually done any of the, it hasn't executed any of the code for the methods that we stored in it. How would we use this package in a DS2 data program? Well, here's the beauty of it. A simple declare package statement makes all of those methods available to my DS2 data program. So here I have a declare package statement. See, this is the place we stored our package, and we give the instance or this copy of the package that we're going to use in this data statement a name. We're calling it M. Now, packages can have constructor arguments. This package has nothing that you have to give it to get ready. And so we just use the open and close parents to complete the syntax and make a copy of the package we stored out here ready to use in this data program. And that copy or instance is named M. So what do I do in order to use the interest method that was stored in my package M? Down here, I reference that method by saying M dot and then the name of the method inside. I give it the parameters just like I did before. Remember that this is acting like a function, so return a value. So we'll use this on the right-hand side of an assignment statement, and we'll assign the results to our variable total. And we can see that this is working exactly the same as it did before, but we didn't have to write the method code into this data statement. We just got to all of that code straight from the package. Everybody is using our package. They're doing their interest calculations the way we desire. And our pointy-haired boss comes along and says, "That's a great job, Mark. But now we have to worry about, Carolina Bank and Trust Company down the road. They're offering their customers interest that's compounded quarterly or weekly or even daily. And as a result, all of our customers are abandoning us and going down the street. So we need you to modify that interest calculation method so that we can compound multiple times a year if necessary." So we talk about how that might look. And in this case, we'll take that same calculation that we're doing, but we're doing it for multiple periods in a year. You only take a fraction of the rate then. So if we were doing it for 12 periods once a month, then you take the rate divided by 12. And we'll do that for every period in the year, and we'll do that whole thing for every year that we want to keep the money. And that will give us a nice way of compounding the interest more than once a year. Now the problem is we have a package out there with an interest method in it, and that interest method only requires 3 parameters. Our new method is going to require 4. And user-defined methods can't accept a variable number of arguments. So if we change the interest method to require 4, everybody who's using our package out there, they're going to crash and burn when they run their code the next time. If we don't change it to be able to use 4 arguments, of course, our boss is going to be angry. Maybe we'll get fired. So what can we do? You start to feel the pressure, start to feel a little bit overloaded. Okay, I'm sorry for the joke. I don't know who gave the term overloading to this, but it sounds like something horrible, doesn't it? Overloading a method sounds like you're about to break something, but it's not horrible. It's actually a wonderful idea. Basically, when we call a method, we called it by name, but I was kind of playing fast and loose with that concept. When you call a method, You call a method by its signature. And the signature consists of the name of the method plus an ordered list of the data types that it uses as parameters. We can clearly see that the method test with one real parameter is different than the method test with two real parameters. So this is the concept of overloading methods, writing two methods with the same name but distinctive signatures. Now we talk about data type, but it's really closer to a data class type thing. For instance, DS2 won't be able to tell a difference between a real and a double. They're floating point types. So if you made one with a single parameter that was real and one that a single parameter that was double, might have a little trouble distinguishing that, right? So think of this as signature test, floating point, floating point, right? If you get two or more same name methods with the same signature, we get an ambiguous method definition, and that'll throw an error when we try to call the method. When we call an overloaded method, the first thing that happens is the signatures are compared to the number of parameters in each method that has the same name. And if there is no match by number, say we had, go back to our original method here, say we had test with one real, test with two reals, and then we called test with three reals, there's no definition that has three in it. And so that would fail, and that would be an unknown method definition. But if the number of parameters matches, then we look for the closest match by data type. And if there's an exact match, that's great. The method is called, the values are fed to it, and it executes. If there is no exact match for data types, then the parameter data types are evaluated, and the input data is evaluated to see if they're coercible. And if there are coercible data types, then the values are coerced to the appropriate data type for that method, and then the method executes. So an error will occur whenever the number of parameters doesn't match any of the signatures, or when the method signatures are ambiguous, or when the data types that you call the method with are not coercible. So for instance, with our method that had one real parameter, if we called it with a date, an ANSI date input, dates are not coercible, and so you would have an error. So this package contains two definitions for the interest method, one with the traditional 3 parameters of input for an annual compounding, and one that allows 4 parameter input for a multiple compound per year. And so we can then recompile or recreate the MyMethods package. Now there's actually 2 interest methods in there, and you can use either one by merely calling it with the right number of parameters. So let's take a peek at a slightly more complex algorithm that we might benefit from putting in a package. This is a DS2 data step that is designed to score our campaign table. And basically, we're going to declare some variables here, the score variable, which will give us the score for the particular individual that we're scoring, and a count, so we can keep track of how many records have been scored. Now, there's some documentation here that basically tells us what variables to input, which are the inputs to the scoring method. And you'll see the beginning of the method definition here with all the inputs in. This is returns a double precision value for the answer. And you're going to see that there's a lot of code here. This code was generated by Proc HP Logistic. So without further ado, let's go down to the bottom and see the end of the method. And so here's the end of the score method and the return statement that returns the scoring value. Now the instructions gave us information on which variables in the campaign data set we should use as input. And so we're going to use those values as input to the score method when we call it. We're going to keep track of the number of rows that we score using this count variable. And at the end, we're going to write out some statistics. Now, this is a DS2 data program, so it is single-threaded. So we don't expect anything odd or unusual going on here. But thread ID is an automatic variable that identifies the thread running this particular piece of code. For the DS2 data program, we expect that to be 0. Nthreads indicates how many threads were available to DS2 as the process was running, whether or not we used them. And underscore count is that count that we've been using to count up the number of rows we've scored. So if we run this program, we should be able to score this campaign data set using our scoring algorithm. We see that we processed 106,000 rows pretty quickly. The data program is writing the results out to DS2 SAS scored. So let's see if we can find the scored table and take a quick peek to see that we are getting a different score variable for each ID in the data set. So that seems to have worked pretty well. Now, what if we wanted to use this algorithm to score this data set or others like it many different times? Writing all that code into the data program would be kind of a pain in the neck. I would prefer to do something like this. Have a package with a scoring algorithm in it, and then just call the package, the score method from that package. So in order to do that, we're going to need a package program. And what I've done is I've extracted the code for the scoring method from the data step that we used before, and I'm putting it into this package statement. I'm going to store this out in a DS2 package underscore scoring in that same SAS library. And you'll notice that I've actually written a couple of versions of the scoring method. So this package contains the following method. This is a contents method. It doesn't take any parameters. It's just going to write some stuff in the log. And I do this with every package that I make. I make a method called contents, and I keep it up to date by hand. So as I add methods to the package in the future, I'll be able to tell what's in the package. There's no automatic method for getting the contents of a package out. And then the score method itself, I've overloaded. I have one version of the method that doesn't require any parameters, and all it does is write syntax help to the log. Okay. This is actually for the campaign 1 data set. And so if I call this method score without any parameters, it will tell me how to use it in the log. And then finally is the second version of that score method that has the actual inputs and does the actual scoring. And that's the end of the package. So I'm going to go ahead and create this package. You see, that didn't take much time because package really isn't doing any work yet. And if you look at the package, you'll see that it doesn't appear to be very interesting. Actually, when you open it, you're going to be disappointed if you're trying to decode what's going on in there. This is just encrypted source code. So that's how it's stored. And this here is a CRC that makes sure that nobody fiddles with the encrypted source code to change anything. So it's a nice secure way of being able to share algorithms with other users without them necessarily being able to decode how it was done inside. All right, now to use that package, I can go back and in a DS2 data step, I'll just declare an instance of the package. Now let's say this is several weeks from now and I don't remember what's in this scoring package. So I could just declare an instance and call contents to see what's in there. And because I've built the package to be self-documenting with the contents, in the log it tells me, hey, there's only 2 methods in here, the contents method that you just called and the score method. And I say, well, I wonder how that score method works. So I'll run another quick data step that calls the score method without any parameters. Remember, I had made that particular overload so I could get information out. And I run that, and it gives me in the log all the syntax for using the score method. So for campaign 1, it tells me the names of the variables that were built. So that's that's good. To score campaign 1, then all I would do is declare instance of the package, declare my score variables like I did before, and call the score method from that package. So let's go ahead and rerun this again. And just like that, we're scored again. Go down and check the scored data to make sure it all looks kosher still. And so, without having to rewrite all of that code, I've been able to score the data set in much more compact manner. Now, what would happen if I was scoring a different data set? Let's take a look at the campaign data set. And you'll notice that it has different named variables. So it still has an ID, but the input variables are named differently. So let's see, there's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That looks about right. So let's go ahead and feed those variables in instead. And we'll change this to the scoring the campaign data set, and we'll call this scored campaign. Now the campaign data set is a lot bigger than the others. You can see that it has over 1 million rows, but that seems to have gotten scored just like we had hoped, right? And if we look at the scored campaign data set, it has the same types of output that we're used to seeing. So I've been able to take that scoring algorithm that was actually written for one data set and use it on a similar data set, even with different variable names, to conduct scoring. That's a pretty useful thing to be able to do. In the scoring demo, the processing looked a little intense, and perhaps that might benefit from a little threading. Remember that there are 2 basic types of bottlenecks that we encounter in our processing: input-output bottleneck, and this is when the rate at which the data can be read in is slower than the rate at which it can be computed. And this means that the CPU is often idle while it waits for the next record to be presented to it for processing. This is inefficient use of the CPU, and it's quite common in single machines that you have at home because they have a single disk, and the throughput has been improved radically over the years, but it's still a lot slower than moving data around in memory. On the other hand, the things that we do to our data is becoming more and more complex. And so it's not unusual nowadays to run into a process now and again that the calculations are so intense that they can't be completed before the I/O system could have presented you with another row. This is a process that we refer to as CPU bound, because the CPU is still crunching on the one row while we have plenty of other rows available. A CPU bound process is inefficient in I/O. Now, modern computers have multiple CPUs, and most of those CPUs themselves are capable of handling more than one process at a time. So each of these processes that the CPU can pay full attention to is called a thread. We can use threading with I/O, particularly if we have more than one disk, in order to read data in parallel so that the data moves into RAM more quickly. And this allows the CPU to process more continually. And as we use threaded I/O, it becomes more and more likely that the process will be CPU bound. Now, with a threaded I/O, there was nothing I had to change about my program. My program was still reading and writing from a single thread. It was just being moved into memory in parallel. When I have a CPU-bound process, this is different. If I want to process more than one row at the same time using separate threads, I will have to rewrite my application in order to take advantage of all those multiple CPUs. But if I do this, it can allow the I/O to move more smoothly. SAS has been working on this threaded processing for years. All the way back into version 8 of SAS, we were doing things like proc sort, proc means, using multiple threads for things that are CPU intensive. Proc report and many others are indeed multi-threaded processes, but the data step itself is single-threaded, except for when you sort the data for indexing. And if you think about it, that kind of makes sense. The data step is instructions on what to do to an individual row of data. You'd expect that it would process single-threaded. And in a single-threaded environment, anything that we do that's compute-intensive can easily become CPU-bound. So we might wonder, what kind of programs would tend to be CPU-bound and benefit from threading on the SAS compute platform? And more importantly, even if we suspect it, how can we tell by looking at the SAS log after we've run our code whether or not the process is indeed CPU-bound or I/O-bound? Well, the quickest way to tell if your process is I/O-bound or CPU-bound is to take a look at the SAS log after your program is run. In this program, we can note that the real time is 50.34 seconds, while the CPU time is only 4.06 seconds. These two numbers differ by an order of magnitude. Because the real time is greater than the CPU time, it's pretty obvious that this process is I/O bound and unlikely to benefit from threading on the SAS compute platform. Now, this process has a real time of 5.23 seconds and a CPU time of 5.52 seconds. Because the real time and CPU time are so close together, there's a good indication that this process is indeed CPU bound and would benefit from threading on the SAS compute platform. DS2 was designed for threading from the ground up. Writing DS2 threads is easy, and when you use DS2 threads, you can process multiple rows in parallel from a data program. Thread programs are a lot like DS2 data programs. They can declare and use packages. They have to have the init, term, and run methods in them. They can use a set statement to read input. They're capable of bigroup processing, including first dot, last dot, and any global variables declared in a thread will be in the program data vector of the data program that utilizes the thread. The data program is required to make the threads execute because the threads are just a stored program, so to speak. And the thread itself can't make another thread execute. There's a special statement called set from that we use to execute threads, and that set from statement is not allowed in a thread program itself. So in many ways, threads are similar to packages, though, because we talked about them storing in SAS libraries, right? They can also accept parameters and include user-defined methods. And a thread stored in a permanent library, of course, can be reused in a future session. So this is another way of storing complex code for easy reuse. The benefit of using a thread to do so, of course, is that if you store your code in a thread, you can execute multiple copies of that thread in parallel. So this is what a thread program looks like. It begins with a thread statement, and it ends with an end thread statement. It contains global declaratives, and like a data program, any variables declared globally here will appear in the program data vector and in the result set produced. It can include system methods or user-defined methods internally. You can have local declarative statements for locally declared variables, private to that particular method. So very, very much like a data program. Now, when we run the thread program, it stores the thread in a SAS library, much like the package program did. So the question is then, how do we get the thread to execute? We do this with a simple DS2 data program that declares an instance of that thread and then executes multiple copies using a set from statement. Now, while we're threading on the compute server, we'll use the threads equal option to specify the number of threads to execute. Then the threads execute, and as each thread processes a row, it returns that data to the data program. And the data program controls the process of writing the rows to the result set. Now, this is a data program, so you could conduct additional processing on each row of data as it came back from the thread. It's perfectly legal, but you should remember that any processing you do in a data program will be single-threaded. Now, the one thing that it takes a lot of getting used to when you start threaded processing is the idea that when you're running multiple processes that process your rows of data, you actually have no control over the order in which the rows are returned to the data program. As soon as the thread finishes computations, it returns the row to the data program. And this means that every time you run a multi-threaded process, the rows will probably come back in a different order. In the previous demo, we wrote a DS2 data program to score the campaign data set using a scoring algorithm that we had placed in a package. When we executed that program, we found that the real time was very, very close to the CPU time. This indicates that this process is more than likely CPU bound and could benefit from threaded processing on the SAS compute server. So we're going to take that DS2 data program and convert it to a thread. We've changed the data statement to a thread statement. We've changed the end data statement to an end thread statement. We're going to execute this piece of code and create the thread. You notice that that ran very, very quickly, and that's because the thread has stored the program. It really hasn't done any of the work yet. In order to get our thread program to actually score the data set, we need to execute it from a DS2 data program. So here's the data program, once again writing out to that scored data set. Now all of the code required to score that data set, though, is encapsulated in the thread, including the package instance that we're going to use. So all we need to do is declare an instance of the thread. I'm going to call it th, and use that special set from statement to execute the thread. Now when I run it this way, I haven't specified a number of threads, so this runs single-threaded, and the real time and CPU time are very, very close to what we used when we ran it as a straight-up data program. So no benefit yet, but because we have this stored as a thread, now we can execute that in multiple threads at once. Let's try running it in two separate threads with the threads equal option specified. And you'll notice that when we ran that in two separate threads, the real time is now 0.35 seconds. That's cut the real time almost in half for executing this program. And if we work with this a little further, we can boost the number of threads. Let's try 8 threads and see what that gets us. And man, that cut the real time even further down to 0.19 seconds. You notice that as we do this, the CPU time goes up as there's extra CPU required to monitor the processing of all these threads, but the throughput has dramatically improved. And all of this on the SAS compute platform without even thinking about massively parallel processing yet. So threading on the SAS compute platform is all well and good, but if you have available a massively parallel processing environment, wouldn't it pay to try your code up there? Fortunately for us, we have SAS Viya with the cloud analytics services available to us. Now, SAS consists of a series of services that allow you to process data that is resident in memory. In order to process data in SAS, place a data set that's stored in offline storage in memory once, and then process it and analyze it and do as many things as you want to it without ever having to unload it till you're ready. This means that the processing in SAS is extremely fast. And because of the way SAS is architected, you can use data of any size. It doesn't matter if the data is larger than the amount of memory that you have available. Now you can work with SAS from a number of programming interfaces. In this class, of course, we're using SAS Studio on a Viya installation. But you could use SAS Studio over a modern implementation of SAS 9.4. If you're using SAS 9.4 to interface with Viya, you might be using Enterprise Guide as your client, or even the SAS windowing environment. Maybe you're not even using a SAS interface at all. You can do this from RStudio, for Jupyter Notebook, and numerous other ways SAS is normally configured to run on multiple machines. We have the server controller, which will have a series of session controller instances running on it, and several server worker nodes, and each of these will have worker sessions running on them. We communicate with our session controller from our client. In our case, we'll be using SAS Studio and proc DS2 to run DS2 code up on the SAS environment. From the client, we can load data into RAM from offline storage. If you load this from an external source, it's passed to the session controller, which distributes that data across the session workers. In other configurations, you can run SAS on a single machine. We call this symmetric multiprocessing. And in this case, the server controller and the session controller all reside on the same physical hardware, and we get multiple sessions running across the multiple threads available to us on the computer where it's installed. So for example, on my laptop, I have 4 CPUs, which are each capable of handling 2 threads. So it would be possible to run 8 threads worth of processing on my single laptop computer in symmetric multiprocessing mode. In our classroom environment, you have a Windows box with your SAS Studio on it, and we have a Linux server that is running SAS in symmetric multiprocessing mode. SAS libraries and SAS libraries operate a little bit differently. In a SAS library, we refer only to the physical offline storage. When you reference a table with a libref.table name, the SAS system automatically loads that table into memory, say in a set statement, and processes that data. And when the data is done processing, it unloads it from memory automatically. A SAS lib consists of a combination of in-memory space and offline storage. We can load data very quickly into the in-memory space from any of the locally stored data sources. And the data sources don't have to be in just SAS dataset format. They can be in comma-separated values, in SAS HDAT files, Excel files, all sorts of things. In fact, in the data sources, you can actually store access and credentials for reading data in from a relational database like Oracle or Teradata. But before you can process the data, you have to lift that data source up into the in-memory space. Once the data is in memory, it stays there until you write it back out to offline storage explicitly. So the data source area stores connection information and access controls more than just physical files. You can store all of this information there and how to get access to predefined data sources for this particular SAS lib. So when you're running DS2 in SAS, it works kind of like this. First, you have to make sure that the requisite resources are going to be in SAS, because we want everything to run in SAS. And that includes if you have packages or thread programs that you're going to use, those need to be up in the SAS in memory before you try to execute a data program that takes advantage of them. So for example, we want to run in memory. We also need to read from an in-memory table, which means our original thread, which was probably written to read from a traditional SAS library, will have to be rewritten to read from the SAS lib instead. And then if you want the process to run entirely in SAS, you'll want to write the data out to SAS also. This will provide the fastest throughput for your processing. And once you're ready to roll, on the proc DS2 statement, you use the sesref equal option to point to the SAS session where you run your code. To do our processing up on the Cloud Analytic Services, or CAS, we need to make a connection to CAS and establish a connection to the SAS library that we want to work with. Now, this was all really handled for you already in your livenames.sas program. If you look at the code in livenames.sas, it had already set up a connection to SAS named SAS Auto and had designated this DS2 SAS library as the active SAS lib in the SAS session. In addition, down here, we actually assigned a SAS live name to that so you could see the things that were available to you in the SAS lib. And currently, we can see that there's nothing loaded in the memory portion. Now remember, in SAS, the only data that you can process is the data that's already loaded in memory. So our goal, remember, we had to make sure that all the resources we needed were loaded into memory over in CAS before we processed it with a DS2 data program running up in there. Okay, so those two sections have already been taken care of by our live name program. Now here we're going to load data into CAS. Now there's a lot of different ways of loading data into CAS. You could write a data statement and run right up to that DS2 library that we were talking about here, and the data would write into CAS in memory for you automatically. But we have saved the campaign data sets out there in a SAS HDAT format. Now this is a really nice format to work with in CAS because it saves it in such a way that it can be distributed across the different nodes in CAS, and when you load the table, they all load up in parallel. So we're going to load the campaign tables from the SAS HDAT files associated with the CAS lib out there. But the scoring package, I don't want to have to rebuild that. And the scoring package is already available to me here in SAS. So I'm just going to load that up from the SAS side up into the CAS library. Let's go ahead and run the proc cas util. And that loaded that up for me. And now you can see that in my CAS library, I have campaign data sets available to me and my package for scoring. So I have the resources I need up in the CAS library. And all that remains is to make sure that my thread is reading from the CAS table and my data program writes to the CAS table, and that we specify that the session should run in CAS. In order to run things in CAS, we had to say sesref equals CAS auto, or the name of the CAS session. We called this one CAS auto. And I'm writing my thread program up straight into DS2 CAS. It's reading this time from the CAS dataset, campaign 1, rather than the SAS dataset. And just like before, when we run the thread program itself, shouldn't take a lot of time. It's just storing the code right in a thread. It's not really executing that code yet. All right, so now that we have the thread stored in CAS, we have the data up in CAS, we have the package we need up in CAS, we can execute the DS2 data program in CAS. Once again, using the sesref equals auto. To make everything go faster, we're going to write the output to CAS also. Okay, that ran pretty fast. You'll notice that there's an awful lot of nodes available to us in CAS, and that by default, CAS makes use of them all. Without the threads equal option, rather than run single-threaded, when we run in a massively parallel platform like this, then we take advantage of all the nodes. Now you can limit the number of nodes that you use for processing by using a threads equal option, but if you do so, that's going to slow things down because it's going to require that chunks of data be moved from node to node, and so that all the processing can be conducted on only the number of nodes you specified. So I just want to demonstrate that if you do use the threads equal option in CAS, then CAS will only use 2 threads. And you'll notice that last time it took 0.19 seconds. This took a little bit longer to execute. Now, if we look at the old scoring in threads on the SAS Compute platform, the real time there was also about 0.19 seconds. So the original scoring was about the same time on this massively parallel platform. And that's because the data isn't very huge. But what if the data was a lot larger? That last data set that we processed had about 100,000 rows in it. What if we had a data set that was much bigger, say over 1 million rows of data? And I actually happen to have a data set like that available to us. It's called campaign. It's also stored up there in the SAS HDAT format, so we should be able to load all 1 million rows of that data table pretty darn fast. And just like that, they're loaded up into memory. Wow, that didn't take long at all for sure. Now that we have the big data set up in there, we're going to use the same process to score that campaign data. We're going to rewrite the thread so it's reading the larger data set now. And then when the thread's rewritten, we're going to go ahead and re-execute that same data program, scoring over 1 million rows of data. And that's impressive, right? In about 1.13 seconds. And this will vary a little bit each time you run it, but it's always going to be pretty darn fast because we have all of that lovely parallel hardware working on our behalf. That's 1 million rows more than the original data that we were processing. And it only took about 3 times as long to run. All right, and so with that all done, all that's left is for me to clean the system up. And just so you can see how that would be done, you can get rid of tables from memory just by using a drop table statement. There are all sorts of little snippets over in here that you can play with for Cloud Analytic services. They have starter code for you to load a data table into CAS, delete one, to save a table out to the CAS library. So if you're interested in playing with that. But we're just going to clean this up to set it in the condition in which we started. And when we go back and look at the libraries now, you'll see that we have removed all of that stuff from our CAS library. And that wraps up our demonstration. Well, congratulations, you've made it all the way through the lectures for high-performance data manipulation on DS2. And now it's your turn. If you can get access to your virtual lab, go to section 5 of your course notes PDF and follow the instructions there to practice some of the things that you've seen demonstrated in these videos. As you begin your practices, make sure that you do all of the steps of the first practice completely, as these are the steps that set your lab up for success in all of the other endeavors. And then there should be one practice session for each of the lessons that you've seen in order to help you simulate how it feels to program in DS2. I hope you've enjoyed this course as much as I've enjoyed presenting it to you. You have a great day.